Hi everyone, welcome to APCP String Seminar. Let me introduce our speaker Dongsheng from the University of Warsaw. He is postdoc in the University of Warsaw, and today he will talk about the holographic path integral optimization. Please join me in welcoming our speaker Dongsheng.
Thanks for the introduction, Yungi. And it's an honor for me to give a talk remotely to you guys from Asian Pacific Center for Theoretical Physics. So today I'm going to talk about a work that is based on, oh, sorry, there's a typo here. Based on this work with Jan Boruch, Pavel Zaputa, and Tadashi Takeyanagi. So Jan is a student of Pavel here. So let's start on what this topic is about. And to start with, we would like to advertise that this study is actually embedded in the framework that we want to understand quantum states in terms of geometry. So in ADS CFT framework, this correspondence or this understanding is much better and clear. And especially from the work of Hu and Takeyanagi in 2006 on the entanglement entropy. So here is how these things work. Let's say we have a CFT state, which is a vacuum state. And a known fact is that it will be dual to a pure ADS spacetime. So somehow we say the ADS spacetime is like emergent from this vacuum state. So let's say this disk here, this cartoon picture here is like a time slice for the ADS, and then you see that the paths in the middle seems like to be emergent from the boundary, and that's how somehow the slogan saying that the space-time is emergent from the quantum mechanics or the quantum states. There can also be other states, such as thermal states. So this is a mixed density matrix. And we know that it will, the dual geometry or the geometry that can explain this thermal states is a black hole in the center of ADS. And there are also some other states that are interesting to study, for example, coherent state. And the dual picture in ADS is more or less clear. So that's a work that Pavel and I are working in progress. So why am I talking about quantum states and how general this quantum state can be? The things that for usual quantum state, other than the geometric description in the framework of ADS CFT, we can also define it more generally. So the general definition could be used via the Euclidean path integral, or somehow since it's after the work of Feynman, it's also a Feynman integral, Feynman path integral. So let's say we can define a wave functional for QFT or CFT in a general dimension. The definition is as following, that we can start with some reference state, and then we use a path integral or some initial state. We use a path integral. This part is Euclidean, and then we integrate over all the configurations of this field with starting point at phi I and its ending configuration. Final configuration is phi f. So the final state, the wave functional for the final, for the final states will be dependent on the final function of this phi. And here we can also sum up over all the initial configurations. And this picture is, this definition is actually much more clear in 2D CFT. Say we have a 2D CFT on a cylinder. On each time slice, we can have a kind of state or a wave functional defined in each time slice. And we can use path integration to prepare some state at a certain or a given time slice, and as tau evolves. So let's say our initial state here is the vacuum. In CFT language, it means that we insert the identity operator at the minus infinity. Since this is a cylinder, if it's in radial quantization on a plane, that means we insert an operator or the identity operator at the origin of the plane. So the wave functional for the state we are preparing in the cylinder can be written in such an integral form. So that is a general definition of a quantum state. And what can we learn from this definition, and what we want to do in this work? So there are two questions we can really ask in this framework of ADS-CFT. And the first one is exactly what I have said. So what kind of information can we extract from using this tool, from using this path integral way of defining state, and how can we extract this information? So that's the work of those authors in 2017, including Pavel and Tadashi. And the second question we would like to understand in the spirit of ADS-CFT, or in the spirit of that geometry is emergent from the quantum state. And this question is that, can we have a precise gravitational realization of this path integration? And how can we do that? So, and this is the latest work that we have been put out. So those are two papers that has been studying, been proposing how to study this question. So let's probably start with some introduction on the first one to get a feeling how the path integral formalism work here, and what kind of information can we extract there. If you have questions, please feel free to ask. So let's start with the first one. So here we are really considering a Euclidean path integration, and the intuition actually comes from the tensor network. Let's put the setup in a 2D CFT. It's much cleaner than higher dimensions. So in the following, probably my description or my explanation will be purely based on the 2D CFT. And here is what I'm going to tell you. So if you recall that in the previous slides, I have introduced the wave functional that is in a path integral form. And in the path integral form, there are actually some measures. So this measure of the field. And we know in the 2D CFT, or in general in this 2D case, while if two backgrounds are related via a conformal transformation, we know that the measure will actually change accordingly. And the law to change this measure is first given by Polyakov in the 1981. So these two measures are related to each other via exponential to the Liouville action, which I will give you the explicit form later. So this is a known fact. Why am I telling you this about this background change? The reason is that supposing we use this the thing to prepare the state, use the path integral to prepare the state. So let's start with some flat space. That means the grids are evenly distributed in each layer. And at each layer is actually in the time direction. So sorry, this tau should be upwards. It's from minus infinity to minus epsilon. And there is another spatial direction. So the state we prepared, we should be able to prepare is at tau equals to minus epsilon. And there are some certain boundaries conditions for this state. And the intuition from tensor network is the following. So if we count the joint part as some tensors that are living at each joint part, then it tells us to have a good tensor network built in here. And if we want to have a minimal number of tensors in this graph, this tells us that actually we should have a kind of hyperbolic space instead of flat space. So the hyperbolic gradient is somehow regarded as an optimized path integral state. So this hyperbolic space will appear in the later discussion and is very crucial for our understanding in the alias spacetime. Here is just some pictorial understanding and intuition. So this can be made precise in the 2D CFT and the Liouville language. Let's see how this works.
How about the higher dimension? Is it
right?
The,
So in higher dimension, in general, this is not really established. We don't really have such a relation. But in the early works of Pavel and Tadashi and the collaborators, they made some conjecture on higher decays, like how the Liouville-like action should look like. That will still be some curvature terms and then the kinetic terms, but it's not concretely established in higher D, since you see the anomalies will be more complicated than the 2D case. So it's still some question that is we're actually exploring. So in higher D, there is an analog of 2D case of the on the Riemann curvature. So we know that 2D case, we can write the Riemann curvature purely in terms of the conformal factor, while in higher D, so in 4D or even higher, there is some similar stuff called Q curvature term there. But this Q curvature term, say in 4 dimension, so we know that it should have it should have a mass dimension like around of 4, while 2D we see it has 2 derivatives and it has mass dimension 2. So that means in higher D it has more derivatives and it will contain also higher curvature terms in that Q curvature term. So it's still not very clear, but for the purpose today, it probably suffices that we consider we take it, say, let's accept this conjecture that is a reasonable conjecture.
Thank you.
Thanks for the question. So, right, to make it more precise in this Liouville language, we have the passing. We have the wave functional that is defined before, while we need to specify the final state, and then plus the change, like this law of changing the measure under a conformal transformation or a conformal mapping, we will get some, we can substitute this inside, and this can relate two wave functionals that are conformally related to each other. And through this relation, we can actually define a path integral complexity for the reasons I will tell you below. So it is defined in terms of the log of the wave functional at background e to the 2 phi times g hat, and we need to subtract the log of this wave functional at g hat at another background. And the difference of these two log thing will be precisely this Liouville action. And so because we know complexity is actually some kind of distance between states, roughly speaking, or the difficulty how we can go from one state to the other. And in this way, that we can define complexity through the log of the wave functional, it actually have a sense of a directional distance between these two states. By directional, I mean that if I interchange the background between the first state and the second state, and then we will see that we will have a minus sign while we do this changing. And another interesting thing is that it has also some kind of associativity. That means if we have three backgrounds, we compare these three backgrounds with each other. So if we compare first one with second one, and then plus the second one with the third one, actually is equivalent to consider the first one with the third one. So this looks like some associativity for this path integral complexity. Those are the properties of the path integral complexity.
So
It
when
looks,
you say
yeah.
directional distance means that because it's not the positive definite.
Right, it's not a positive definite. So in the sense that it really depends on which background we are compared to which one. If we reverse this comparison, then it will give a minus sign. Say on the left side is positive or definite, but if we define this way, it will not be positive definite. So maybe it would be, if we want a positive definiteness, then it might be defined via the absolute value of this difference. But the price we need to pay is that then the second property will get lost. So this is some tricky property of of this path integral complexity.
Sorry. So if we don't have conformal symmetry, can we generalize this argument to, so instead of like having Liouville action, we use the general Polyakov action? Is that true? Like, can we do that?
Right. So in the if we use the Polyakov action, so that we will have this R box R term, right? And I believe it can still be bring to the Liouville action, and even in that case, since it's still a type of action, I believe the subtraction here still works. If we have a functional, then so it's only, I'm not so sure about this measure part, because when we do a conformal transformation,
yeah, we don't have conformal transformation for the general case. Yeah.
Right.
Okay.
Yeah, maybe, but that's a good question. So the thing is that in 2D, since all the metrics are conformally equivalent, and there is always a procedure to bring two metrics to be conformally equivalent. So that is of course the Beltrami problem. So I think since they are conformally equivalent, and this could be some kind of the most general way to define it. But it's of course an interesting question to consider the Polyakov action. But in some certain cases that probably, yeah. Thanks for the question.
Hi, Dongsheng. I hope to ask one question.
Sure.
Okay. The first, I want to ask, your computation. Do you need to do a epsilon perturbation on your computation?
You mean to perturb the metric?
Not so. I just say why you always have the Liouville term without the epsilon perturbation. because if you consider tensor network, although epsilon is small, but it's still finite. And the epsilon may break the conformal symmetry.
The epsilon contribution.
Yes, otherwise I think that you just do the 2D CFT is not related to the tensor network. Because I think your proposal is discretized tensor network.
And so this part I'm not very sure. Probably you mean when we so this epsilon something is related to this measure part. Is that?
Yeah, maybe. I just said that you possibly need to do a perturbation, but here I found that you just do the CFT computation.
Yeah, here is a pure CFT computation, but I think probably the perturbation you have in mind is really to perturb the background. Is that true? Like we have we put some perturbation in this 2D background. It's like turning on a source for the stress energy tensor in the 2D background. Is that what you have in mind?
Yes, maybe, but I just said that it should be. We should do that. Yeah.
Okay.
Yeah, but if so I said that you may not have the conformal symmetry, and also you may not have the Liouville field theory.
Okay. Yeah, probably I need to. So you're saying it's related to the Teichmüller space. Probably I need to look at that.
Yes.
Okay.
Yeah. Okay. So okay. Thank you. Now I'm understanding. Yeah.
Thanks for the comment. Okay. Thanks for the questions. So let me continue on this past integral complexity. So here we have more or less defined some quantum informational quantity, and now we need to understand what can we do further. So the further thing we can do is to minimize this past integral complexity in some certain comparison. Of course, as Jungi pointed out, it is not a positive definite. But while if through a proper definition, it can be either positive definite or negative definite. And so this further thing we would like to do is to optimize this path integral. And the equivalent way of saying that is to minimize the path integral complexity. So all the stories are related to the Liouville action. How does it look like in general? So here is a general form for the Liouville action. It is actually an integration over the general background, this 2D manifold, and it has three terms: the kinetic term, and then the potential term or the cosmological term, and then the coupling term between the dilaton or the conformal factor to the Ricci curvature of the background. If there will be some boundaries for this 2D manifold, then it will also have some boundary term. So here C is the central charge of the CFT. And to optimize with respect the path integral, we need to do the variation with respect to the conformal factor of the Liouville action. And this constraint will lead to the Liouville equation. So it can be written in this form that equals to 0. This can be easily see from this bulk term that we do the variation with respect to phi. So, but this term is written in the G hat background. If we use the G background to write the equation, meaning that G background is the e to the 2 phi times the G hat. And we can write it purely in terms of the Ricci curvature of the background and the cosmological constant. Since here we really require that the cosmological constant to be positive. And from here, you see that it's actually this equation tells us that the Ricci curvature of this background is negative, is a negative constant. So this means we are actually dealing with a hyperbolic space for the optimized case. And that's my first comment. So this gives us some hint that it should, in principle, related to some ADS slice. And the second comment is that when the G hat is a flat case, so it's like a delta AB, then the equation of motion for the G hat will be simplified as this equation using holomorphic coordinate. And then since we need to impose some boundary condition on which state we are looking at. So in the background, we are actually imposing some boundary condition on the conformal factor. And by solving this equation subject to this boundary condition, we will find some solution that the conformal factor is actually will be 1 over tau squared. So this is precisely a hyperbolic, it's a 2D hyperbolic slice. And in this case, we can calculate, so we substitute this conformal factor into the Liouville action. And by using the definition we have before, which is the Liouville of phi minus the Liouville of 0, then actually we see that the complexity is bounded from below. And this result seems to coincide with the computational complexity result. And the things that here, if we have a type of Liouville action in higher D, so this is not precisely known and is not very solid at this point. But we believe that this should also hold for higher dimensional discussions. But so far, we need to take this part like with caution, since it's not yet very solid.
Can I ask
after? Sure.
Yeah, maybe it's too early to ask, but you have definition of complexity here, and there is two definition, maybe more, but I know only two definitions of the holographic complexity, like action or volume.
Right.
Which one is consistent with this path integral complexity? Or
right, so that's a very important question, actually. So in this part, since we are doing path integration, it looks at first sight that the action conjecture is closer to what we are discussing here, or the discussion is closer to the action conjecture. But things that the action conjecture, so that action is actually evaluated within a certain region. So that is called the Wheeler-DeWitt patch. So it's a certain wedge, bulk wedge. But here we didn't really, so in the later discussion, you will see that it's not really confined to a certain region. But we still evaluate the on-shell action. So somehow I would say it looks like a mixture between the action conjecture and the volume conjecture. But this volume in the original proposal for by Susskind is a volume, it's a co-dimensional 1 volume. But here, since we integrate over the whole bulk space-time, so somehow it's a co-dimensional 0 volume.
So you will you have some slides on that.
Yeah, I will have.
Okay,
that's so. Yeah, let me continue to the second part of this discussion. So the spirit, as I have advertised before, is that we need, or we would like to have a better geometric understanding of states. So the the first part is mainly dealing with a kind of CFT consideration or field theory consideration. And the question in the second part we would like to answer is that what is the gravitational realization of the path integral optimization? And given that we have the hint from the hyperbolic solution, which is the optimized metric in the CFT side. So how do we do it? So the first thing we need to understand is that what is the analog of path integral in the gravitational side? So actually this is known. It's a work by Hartle and Hawking in the 80s. And this analog in the gravitational theory is actually a gravitational path integral. And this gravitational path integral actually defines us a quantum state, which is the Hartle-Hawking state. So I would like to give you a brief introduction of this Hartle-Hawking wave functional. This is actually it's actually very similar to what we have seen before. Instead of some arbitrary field, here we need to do a path integration over, or an integral over the metric. So the Hartle-Hawking wave functional is defined via this formula, and we will have a factor that's e to the minus of the action, and we will have a measure that is the metric. So by integral over this measure, I really mean that it should sum over all the geometries, but we actually need to specify a kind of state that we would like to prepare through this path integral. And in the gravitational language, this is equivalent to say that we fix the induced metric on a given time slice, say time slice. It's actually a Cauchy slice, but not necessarily Cauchy slice, but it's right. We fix the metric on induced metric on a given time slice, and this is some early version of quantum gravity. And there is an equation for this wave functional. It's actually to act the Hamiltonian operator on the wave functional. So this will give us 0 as the constraint. So this equation is actually called Wheeler-de Witt equation. If we look at the Hamiltonian constraint for the vacuum, so it's actually this. So I want to stress that this Hamiltonian has classical form, and it comes from the Hamiltonian constraint of like in the GR sense. The classical form of the Hamiltonian is made of the data on the given time slice. So we foliate it in terms of say time slices of the manifold, and then at each time slice we will have data coming from the induced metric and also from the extrinsic curvature. So the Hamiltonian constraint is written purely in terms of the extrinsic curvature, while it has also to be dependent on the intrinsic curvature on this manifold. So the Hamiltonian constraint puts this to 0 in the vacuum case. And if we promote the extrinsic curvature to be some momentum, so to promote them to be an operator, and through this manner, so this pi ij is the conjugate momentum to the induced metric. And then it can be written in such form, and this conjugate momentum is in the usual sense, in the operator sense, is actually the derivative, the functional derivative of the induced metric. So this is just a short introduction of what is the Hartle-Hawking state. And in our case, how do we realize this Hartle-Hawking wave function in ADS? So that's what we have considered. And let's start from maybe this picture. So in the left region, this is like a Hawking-Hartle-ish wave function. Now we need to integrate our action, and the action we starting from the epsilon at the sigma slice on the boundary, and then we integrate it we foliate our space-time like a Chinese fan that somehow it is open till Q, till the hypersurface Q. So at the hypersurface Q, the boundary metric is fixed up to a conformal factor. And if we put a tension term on this Q surface, it looks really like an end-of-world brane scenario. So the path integral is actually integrated. It's starting from the sigma surface and then opening to the Q surface. And the wave functional for this Hartle-Hawking state is can be written in this way. We know that it's always not. It's actually very hard to evaluate this integration exactly in general dimensions. In 2D, we know for JT gravity, it's easier to evaluate the path integration since it's a topological theory. But in higher D, it's hard to evaluate. So in the following discussion, actually what we are going to do is to use the saddle approximation. The known saddle for this case is the Angle action. So I have talked about this action part in this ADS in the gray region that we are integrating, and the action is actually made of the following parts. It will have the Einstein-Hilbert term, that is the bulk term, and then the extrinsic curvature term or the Gibbons-Hawking term that has to be evaluated at the two boundary surfaces, sigma and Q, and then there is a tension term localized on the Q surface. So this setup is very similar to the holographic BCFD setup that has been understood previously by those authors, and it become hotter again because of the island story that those authors using double holography to understand the island story. Right. So then we need really to get some result from the Hartle-Hawking wave function, and we would like to extremize this wave function as we do before. So here is the way how we do it. When we evaluate the action on shell, and you see that since we fix the boundary condition on Q to be conformally flat, so the action will eventually be dependent on phi, on the conformal factor. And then we need to extremize the Hartle-Hawking wave function, meaning that this equation should be satisfied. And since the induced metric on the boundary on the Q surface is conformally flat, so the only degrees of freedom that one can vary is the conformal factor. That means this equation is equivalent to the trace equation if we do the variation with respect to the induced metric on the of the Hartle-Hawking wave function. So let's use an example to explain the ideas that I'm going to tell you, which should be more clear, like how we do the extremization and what kind of information or message it can give to us. So let's start with the Euclidean ADS D+1 in Poincaré coordinate, which we know is of this hyperbolic form. And say, let's parameterize our Q surface in terms of this function. So that is written in purely in terms of f tau, this kind of uniform embedding. And we see that this f function will be related to the phi function in different coordinates. So conformally, on the Q surface, the induced metric can be written in this form. We don't really change the other coordinates. That's why it's called uniform embedding. if we substitute such a metric in the action, in the action that we would like to evaluate, so it contains the Einstein-Hilbert action and then the tension term. That's the result we can get. The first term is actually the divergence coming from the volume of the sigma surface. And then the second term coming from, mainly coming from the extrinsic curvature and the tension term. So the extremizing condition, meaning this equation goes to 0 and delta psi over delta phi goes to 0, actually give the second equation. And what's very interesting here is that this term here is precisely the extrinsic curvature on the Q surface. So this equals to a constant that is dependent on tension. This is telling us actually we are working in a constant mean curvature slice since the extrinsic curvature is a constant. And that is very interesting. And because of that, we can now foliate our space-time purely in terms of those constant mean curvature slices. Looks like in this way. And on each slice, we will label it with an angle, theta 0, say, and then the theta 0 will be related to the tension of the brane, or to the tension parameter. And we see that through this relation, when t goes to 0, actually sine theta 0 will be 1. That means theta 0 will be pi over 2, and this tells us it will be perpendicular to the boundary. So there are a few comments I would like to make here. The first comment is that the tension parameter, there's a typo, it's tension. Tension parameter T actually acts as emergent time. And since at each slice, we can label it with a specific tension parameter, and it looks like, and we are also integrating like from sigma to Q. So it looks like a time direction from sigma to Q. So this looks like some kind of emergent time. It has a time sense.
So here, when you say time, it's more like a Holographic normalization or like a radial quantization, that the radial plate of the like Euclidean time. Is that the similar?
Right. That's what I would like to say.
Yeah. So tau is the still Euclidean time in the boundary.
Right. Tau is the Euclidean time in the boundary, and on the Q surfaces, there is this W coordinate that I have shown before, that actually plays some kind of role of time along the Q coordinate. And that's actually this point I would like to say. So we see in this foliation, we actually would like the Q surfaces intersect with the sigma surfaces at this specific position. And that this is equivalent to say that this conformal factor will have this boundary condition when W goes to 0, then it will be 1 over epsilon squared. So it looks like we are always preparing state from every slice, say in each slice from infinity till this place, that when tau goes to 0 or W goes to 0. So it all reaches to the same state. From a tensor network picture, it's like we have tensor networks that are building in each time slice, each hyperbolic slice, and we are always preparing the state from, say, infinity, and then using this intuition to prepare a certain state till this joint part with the same boundary condition. And then by solving the extremizing condition subject to the boundary condition, we will find the surface. So we know already it's a hyperbolic surface, but the precise way of writing it is in terms of this surface equation. So that will be a linear function of tau on this hyperbolic slicing. And when tau goes to 0, it will be located at sigma. So that satisfies the boundary condition. So far, it looks everything is fine, but there's one concern is that since Q surface and the sigma surface, they actually intersect at this joint part, and this part is not necessarily smooth, and in fact, it is not smooth at all. So somehow, it seems like we need to consider a Hayward term, which is the corner term. But since it's a boundary term, it's a corner term, it doesn't affect the bulk equation of motion. So this solution still holds, and not surprisingly that it also obeys this boundary condition. Right, so on the next step, we would like to consider this Hayward term, and we would like to make some proposal, like how holographic complexity could look like in this pass and grow picture.
So in the DCFT case, that is the place where this boundary of the CFT lives.
Right. So sigma is where the boundary of is where the boundary CFT lives. Boundary conformal.
But so what is the boundary of the CFT? That point, that the corner is the boundary of the CFT.
Right. It's the boundary of the CFT. Okay. Exactly. So this joint part is the boundary of the CFT. If we will have a conformal field theory on the boundary, so the easiest boundary condition is to consider that this boundary of the conformal field theory to also be a conformal field theory. So it's a boundary conformal field theory. That's in the usual BCFT setup. Right.
Thank you.
So here is the proposal that we want to define this complexity from the Hartle-Hawking wave function. The procedure is the following. So first we need to understand what is the role played by the tension. So the tension here, we are actually thinking it in terms of a calibration. What does it mean? It means that it tells us where till which place we integrate our action till which slice we integrate our action. So we need to introduce this tension term initially, so that we will extremize the Hartle-Hawking wave function and fix the place where we are integrated to. So that is the solution is given in terms of this equation. And then after we have extremized the Hartle-Hawking wave function, we have fixed this slice where we are integrated to. Then we need to evaluate the wave function without this tension term. The reason we don't want this tension term is that we don't really want to include in any matter in the geometry we are considering. So we're really using this tension term as a calibration. So if some brain, like people who specialize in the brain construction might might criticize this part, like why do we evaluate the wave function without the tension term while doing it initially with tension term? So here the story is more like we want to find a complexity proposal from the wave functional. And since here we really don't want to include this localized matter, so or localize the energy flux, so we take it away. And somehow a similar consideration has been done by Lekovitz and Mendesena in their holographic way of understanding Brainy entropy. So there, instead of subtract the codimensional 1 brain term, they actually subtract like taking out the codimension 2 brain term, which is a cosmological string. So in the quantum information perspective, it seems like it's eligible to do that. It is legible to do that, but the reason is not very clear yet. So let's take it as for granted. And then we need to add the non-smooth contribution, which is this Hayward term. And in this work, we're actually adding a modified Hayward term in the following sense. So the usual Hayward term is this theta angle that we need to integrate over the joint volume. And how is this theta angle defined? It's actually defined as the opening angle between the two normals. So these two normals are perpendicular to the Q slice and the sigma slice. But since we want, in our case, when theta 0, like when Q slice coincide with sigma slice, we want this term to contribute nothing. So here we actually add a constant to the Hayward term, which is -phi. So it's the compensating angle of the capital theta. And this procedure doesn't affect the variational principle if we impose the Dirichlet boundary condition on this joint part. So this doesn't really affect the variation, and it will suit our purpose. And then following this procedure, if we summing up all the terms we have in the vacuum case, we'll have our kind of desired complexity. So this complexity is defined, is evaluated in terms of the Einstein-Hilbert term plus the extrinsic curvature, and then the modified Hayward term. It will have, roughly speaking, two terms. The first term, as I said before, is actually the volume of the sigma slice, since it's a conformally, it's actually a flat, but with 1/epsilon squared as the total conformal factor. And by analyzing this result, it's easy to see that the minimal is achieved when t equals to 0, when the tension parameter is equals to 0. So to remind you, the tension parameter is related to the angle theta 0 via the following formula. So this result here is monotonically decreasing when theta goes from -infinity to not -infinity, -d-1 to 0. So somehow this is achieved. It's not that surprising though. The reason is that it seems like what we want, because if we consider, say, in a global time slice, right? Global coordinate, then the extremization condition actually leads to that we prepare a state at tau equals to 0 in the global slicing. So this somehow is reasonable. And the properties of this type of complexity, it also satisfies the two properties that I have presented before for the CFT side. First one is that if we interchange the metric, then we get a minus sign. And the second one is this associativity. The second equality is easy to see. Is basically, it is a result of the additivity of the action. So say if we integrate what we have here from sigma to q, and then from q to some q prime, actually equivalently, we can integrate from sigma to q prime. And that's because the action can be added together if these two manifolds are smoothly glued. We have also done some other examples in this work. So we have some excited states in ADS3, and we have also done JT gravity. And we also have some Lorentzian signature for ADS and DS. So I will not talk about that. But the thing for all the cases is that the space-time will be foliated in terms of a constant mean curvature slice. And here I would like to make this comment further. It's like, first of all, this tension parameter actually quantifies how deeper we go inside into the bulk, as I have shown in the previous slides. And to talk about this emergence of time, it seems like since in all the cases we have studied, the slices, they all have constant mean curvature. And for such kind of geometry, we can actually use a warp geometry, this warp geometry to describe this manifold. So we will have a kind of angular coordinate that is, so this looks like an angular coordinate in the Poincare slice. And then this warp factor is warping around the internal manifold like this, each hyperbolic slicing. So since this warp factor here will be dependent purely in terms of rho h, and then this gives us a sense of emergence of time. Let's give some summary of what we have studied and also some outlook on what can be studied. So we have in this discussion or in this work, we have made a step towards understanding the gravitational, the analogous, the gravitational way to understand the CFT passing growth optimization. And we also proposed for a holographic complexity from the extremization procedure of the Hartle-Hawking wave function, though the relation between this holographic complexity proposal with that of the action proposal and the volume proposal in a few years back is not entirely clear. It looks like a mixture of the two. And the third thing is that in all the examples we have considered, it looks like the space-time is foliated in terms of the constant mean curvature slices. And there is some emergent time discussion. So it would be interesting to understand how this time would be related to the York time that has been advertised by the work of Belin-Lekovich and Sarosi 3 years ago. And since we also talk about the Lorentzian case, and we know that this Lorentzian case, the path integral, there is always problem in defining the path integration. So can we have a better understanding of that? And what will be, is there some clue to understand the DS CFT correspondence better since it's less explored? And will there be some other geometries, like some other solutions that have similar properties, such as that they are foliated in terms of this constant mean curvature slices? And there could be many more interesting questions to explore. Thanks for the listening.
Thank you very much for the very clear and nice talk. Please ask a question.
Hi, Dongsheng. I have one question. At first, thank you for your good talk. At first, I think that your derivation of the is very similar to deriving the real field action from the metric formulation of a 3-dimensional Einstein probability theory. I guess so, if I do not misunderstand your derivation. So if I extend your study to the gauge formulation, should I still use the real field action, or I should use the non-conformal theory?
Okay, so you are saying if we are still talking about 2D theory, right?
Yes. So yeah.
So you're saying if we break the conformal symmetry, then Right. I think.
Sorry, no, it's a little different because I do not break conformal. I do not break the conformal symmetry. I just talk about you extend your study to the gauge formulation. The boundary theory is not a conformal field theory. So, and the classical limiter is still a real field theory. But should I use the boundary theory to replace the real field theory?
Okay. So first of all, I'm not familiar with this procedure when you have a gauge theory. So you're probably still talking about probably not Chern-Simons formulation, or it's still Chern-Simons formulation.
Yeah, Chern-Simons formulation.
Okay. So right. So you're saying that if the boundary is there, so the Liouville theory, the conformal theory will be a limit of a non-conformal theory once you take some certain limit. And so if it's outside the framework of ADS CFT, then my guess, so I'm not very familiar with this topic, but my guess is that yeah, we can consider some non-conformal formulation, but like some non-conformal setup. But then, like, which physics question we want to extract here? If it's still like we want to extract about some quantum information definition, some quantum information quantities such as complexity, then probably we need some to consider how to define it or how to extremize. If we are still in the spirit of extremizing some wave functional, then we need to understand how to extremize this non-conformal field theory. How is there some trick? Because you see that the Liouville theory here is more or less like a trick that we can understand how to extremize the wave functional.
Okay.
So
yeah, but I would say, how about JT also?
So in JT gravity, the gravitational understanding is much clearer. It's basically a topological theory, and in the CFT side, since it's like a 0+1 quantum mechanic theory, so there has been some proposals to understand that. But if we want to put in the framework, in our framework, then probably then we need to deal with how to define this complexity in terms of, say, matrix theory. So matrix theory is the one candidate of the conformal field theory in the CFT side. I don't know if one can also define it with respect to the
but if you just consider a conformal field theory or conformal quantum mechanics, you can just study a large C order, leading order.
In the large C, yeah. So if it's so the CFT here we are thinking about is really it really has large central charge. So that makes it holographic.
Yeah, but if you want to study the full information of JT gravity theory, then you should not have the conformal symmetry.
If we want to consider the full theory of JT gravity.
Yeah, because what they say is not a conformal field.
Okay. Yeah, I'm not quite sure about right, because so far there are some proposals on the conformal on the duo of JT gravity, which is like this Stanford Schenker work that talks about the matrix theory. But you see that there's a lot of problems, or the quantum mechanics we know it only works, or the conformal quantum mechanics we know it only works in some certain limit. And so like it's a low energy limit of the dual theorem. So I don't have more thoughts on this regard.
Okay. Thank you.
Thanks for the question.
Yeah. Other questions? Actually, I have a question on this de Sitter. You in the previous slide, you mentioned that this de Sitter.
Right.
So can you shortly explain the case, because
Sure. So right, let's see these two cases. One is anti-de Sitter, and this is de Sitter. So we are really consider some Lorentzian case, and the result is still as before. It will have some hyperbolic slicing, but since it's Lorentzian case, then we will have two different regions, so that one space-time one slice will be time-like slice. So these blue slices will be time-like slice, and the green slice will be the space-like slices. And when they are infinitely boosted, so it will be along the red dashed line. And here we can still do this calculation, like to integrate from the boundary till some certain slice. And
so here,
yeah.
This would correspond to some vacuum. So it is correspond to the so-called, what is the vacuum?
It's still the vacuum case. It's a pure.
Like in de Sitter, yeah, there is some Bunch Davis vacuum or something like.
So okay, right. That's a deeper question. So here we actually didn't think that far. We didn't consider whether if there is a well-defined de Sitter vacuum for this theory. We are purely using the geometry, that the de Sitter geometry, to do this calculation. And the reason is that the de Sitter case is not yet understood, and it's not very clear how to really define the CFT. There has been some works before. I remember that, like, we can say the CFT lives at the past infinity or the future infinity of the de Sitter space-time, where you can still have a kind of time direction. Sorry, that is the Euclidean CFT. Sorry. And so here we are not really dealing with that deeper question, and I think it's still under debate whether we can find whether the vacuum of the de Sitter space-time is well defined in a string theory setup. So that is a very deep and hard question, and which is we don't want to attack that for this work. It's more like from the quantum information theory side to see what can we learn in the geometry. But that's of course a very, very important question, and hopefully it can have some people can reach some common conclusion in the future.
Okay. Yeah. Actually, yeah, I have one more question, but yeah, probably it's maybe not that relevant in your talk, but here you consider the path integral where you fix the topology of the geometry. But when you consider path integral, you can also consider the insertion of like some other other summation of other topology. Like for example, one example is this JT gravity. When you in the JT gravity, when you obtain this random metric behavior, you insert this Riemann surface, attach the Riemann surface, and you sum over this genus insertion of the many other Riemann surface, and to get the genus expansion. Actually, it's a non-perturbative like correction. So here,
right. Yeah. So here, when we talk about the JT gravity, our mind is really very naive. We just use the the Riemann surface of the genus, I don't know, genus 2 or genus, like the lowest the genus without any handles. We use that geometry to do to calculate this action, but it's definitely, it sounds quite interesting now. Since you mentioned about that, I think it might be interesting to see how this can be done, say, in the full JT gravity, because we can really do this path integral in JT gravity part by summing all the topologies. So right, that's a very good.
Here, this is a set of approximation, so I don't know how far such a correction give us some meaningful results. But anyway, yeah. So just I was curious.
I mean, that's a very interesting thing actually, because in JT we don't really rely on saddle approximation. I think it can. It should be able to be integrated completely, and the way to get it, since JT gravity is really, it has fixed background, and then we just need to sum up all the topologies. And yeah, it's interesting. I haven't thought about that before. Yeah.
Thank you very much. Is there any other question?
I have one question. So for your second question, at first I thought that I'm trying to check out whether the Liouville action will satisfy the Hamilton-Jacobi equation as the saddle point. So saddle point from the Hartle-Hawking wave function. So then my question is, Liouville action can be regarded as a solution of Hamilton-Jacobi equation from the saddle point of the Hartle-Hawking wave function?
Yes. The question is that whether this constraint comes from the Hamilton-Jacobi equation.
Yeah. So will you show the real part of the Hartle-Hawking wave function? Maybe separately later. Yeah. Yeah. Here. So in the last line, if you pi ij, so in this equation, this is nothing but Hamilton-Jacobi equation. Pi ij is just variation of action, on-shell action of the extrinsic metric, let's say hij.
Yes.
Then, then my question is, the Liouville action can be regarded as a solution of this constraint equation. Can you confirm it, or?
Okay, so in 2D, so you are thinking if we treat the 2D
that's
theory,
the most straightforward way, in my opinion. Yeah.
Right.
Yeah.
The 2D as a gravitational theory, then we still apply this Hamiltonian constraint and the momentum constraint for this 2D theory.
Yeah, from 3D, we have some Hamilton-Jacobi equation to determine the effective on-shell action. Yes, like this one. Yes. Then I want to claim the Liouville action would be a solution of. I'm not sure. That's my question.
And so let's see. In 2D, so basically we are thinking in terms of the gravitational setup, right? And we are thinking that the 2D gravity theory, and now we still foliate it in terms of Hij, and we will have on each time slice we'll have an induced metric, and we will also define the conjugate momentum to it, and then this Hamiltonian constraint will become the Liouville equation. This might be true, but it's not entirely. So how many equations do we have in 2D case?
I'm sorry, I don't know.
Hamiltonian equation. Yeah, I'm just thinking will there be extra constraint equation? So Hamiltonian equation is of course there, but this momentum constraint, yeah, I was thinking there are two equations actually, because there is Hamiltonian constraint, and in principle there is also a momentum constraint that is conjugated to the spatial direction. This Hamiltonian constraint is like for the time direction.
Yes, right.
So
Oh, extra.
yeah, I need to check that, because yeah, the equation doesn't seem to match if I count naively. We have two equations using this.
Well, as far as I know, the momentum equation is nothing but the conservation law. I think usually, yeah.
Okay, so you are saying that
diffeomorphism invariance, blah blah something, yeah. And then the momentum part, yeah, h mu.
okay.
So yeah.
Okay, yeah, that might be possible. I need to check, but that's a good point. I didn't think in that way. Yeah, it's a good point. Thanks.
I see. Okay, thank you.
Mm-hmm.
Is there any other question? If not, let's thank the speaker again. Thank you very much.